You're about to witness how China constructed the largest container ship ever made. A vessel stretching over 1,300 feet long, weighing 220,000 tons, built in just 18 months. This isn't about shipping or trade. This is about the engineering madness required to physically assemble something this massive without it collapsing under its own weight. And it started with a problem that seemed impossible to solve. You can't build a ship this size as one piece. The steel would warp, the measurements would drift, and the whole structure would fail before it ever touched water. So Chinese engineers did something radical. They broke this 1,300-foot monster into over 100 separate megablocks. Each block weighed up to 1,200 tons. Picture a piece of a ship heavier than 10 fully loaded Boeing 747s, and they built all of them at the same time in different assembly halls across the shipyard. But here's where it gets terrifying. When you finally bring these blocks together, they have to align with millimeter precision. We're talking about football field-sized chunks of steel that need to fit together like puzzle pieces. One misalignment, just one, and you've created a structural failure point that could rip the entire ship apart in open ocean. And there's another nightmare. As welders join these blocks, the heat changes the metal's dimensions. The steel expands. Your measurements shift. What fit together perfectly an hour ago no longer matches. So they built climate-controlled assembly halls, massive structures where temperature stayed constant to the degree. They installed laser measurement systems that tracked every single dimension in real time, catching shifts before they became problems. And they created digital twin models, virtual copies of every block that predicted exactly how the metal would expand during welding. The computers told the engineers where to compensate before the welders ever struck an arc. But building perfect blocks was just the beginning of the problem. Those blocks needed to be made from something that could handle forces no ship had ever faced. The hull alone required 80,000 tons of steel. But you can't just use ordinary steel at this scale. When you build something 1,300 feet long, the ocean doesn't hit it like a flat surface. Waves create bending forces that try to snap the ship in half. Traditional steel would crack under that kind of stress. For China, the nightmare was this. Make the steel thicker, and you add so much weight the ship becomes too heavy to float its cargo. Keep it thin, and the hull fractures at stress points. And every time you weld standard steel alloys together, you create weak seams that become failure zones under pressure. You're essentially building a crack into the structure. They engineered a completely new, ultra-high tensile steel alloy, stronger than anything used on previous container ships. But the real breakthrough was how they applied it. Computer algorithms analyzed millions of stress scenarios and created a map. The hull wasn't uniform thickness. It varied across the entire structure. Thicker exactly where forces concentrated, thinner where they could save weight. Then they abandoned traditional welding. They used friction stir welding, a process that creates seamless joints by mechanically bonding the metal without melting it. No weak seams, no cracks. And they built in stress distribution technology, strategic reinforcement points that spread forces across the hull instead of letting them concentrate. Then came the most devastating challenge of all. You've got over 100 blocks, each one weighing up to 1,200 tons, and now you have to join them together. The shipyard deployed massive gantry cranes, some of the largest lifting machines ever built. These cranes had to lift blocks heavier than entire buildings and position them in a dry dock with absolute precision. And the sequence mattered. You couldn't just randomly stack these pieces. Each block had to connect in a specific order, or the structural integrity of the entire ship would collapse. But this was just the beginning of the nightmare. The cranes needed to position these 1,200-ton blocks with an accuracy of 2 millimeters. 2 millimeters. On a piece of steel the size of a basketball court. And here's what made it worse. These blocks had to connect while supporting their own massive weight. If one block shifted even slightly during positioning, that misalignment would cascade through the entire structure. Every block placed after that would be off. You'd build the error into the ship permanently. They developed a synchronized lifting system, where multiple cranes were controlled by a single computer. GPS-guided positioning accurate to 2 millimeters tracked every movement. Hydraulic adjusters made micro-corrections in real time as the blocks descended. And they used real-time laser scanning during the actual assembly, measuring the position constantly as the cranes moved. When the blocks finally connected, robotic welding systems completed over 9 miles of seams per block. Machines working 24 hours a day, 7 days a week, because human welders couldn't maintain that level of consistency. For Chinese engineers, the bigger problem wasn't joining the blocks. It was building the foundation that would carry all of them. The keel, the backbone of the ship, had to be laid first. This wasn't just a flat piece of steel. It was the structural foundation that would support the weight of 24,000 containers stacked 7 levels high. They built a double hull design, 2 layers of steel with space between them, to distribute forces and prevent catastrophic failure. And inside, they constructed an internal framework, a skeleton of steel beams running the entire 1,300-foot length. Then came the most devastating engineering problem of all. The hull had to flex. When this ship hits ocean waves, the entire structure bends. It has to. If it stayed rigid, it would snap like a dry tree branch. But you've got framework carrying the weight of 24,000 containers, and you've got connection points where that framework bolts to the hull. Every single one of those connection points is a stress concentrator, a place where forces multiply, a place where cracks start. Chinese engineers ran finite element analysis, computer simulations that tested millions of stress scenarios, every possible combination of wave height, cargo weight, and hull flex. The computer told them exactly where to place reinforcements. Not guesswork, mathematical certainty. Then they deployed automated welding robots working around the clock. These machines completed welds human hands couldn't match for consistency. And every critical weld, every single joint that mattered for structural integrity, was verified with X-ray inspection. They could see inside the metal, spot microscopic flaws before they became fractures. And it wasn't just the hull that had to survive these forces. 18 months after the first piece of steel was cut, every block was in position. The final mega block, a 1,200-ton section containing the bridge and navigation systems, was lifted into place by synchronized cranes. The robotic welders completed the last 9 miles of seams. X-ray inspection verified every critical joint. And then came the moment that would prove if any of it actually worked. They flooded the dry dock. Controlled valves opened, and water rushed in around the hull. You're watching 220,000 tons of steel that's never touched water. If the calculations were wrong, if a single weld failed, if the stress distribution was off by even a fraction, the ship would buckle under its own weight right there in the dock. The water rose, higher. The hull began to lift off the supports. And it floated. The entire structure held. Not a single crack. Not a single failure point. The ship carried its own 220,000 tons perfectly. But here's what made it truly devastating. This wasn't a one-time achievement. China's shipyards turned this into an assembly line process. They can now build these ships, the largest container vessels ever constructed, in 18-month cycles, one after another. The precision engineering that seemed impossible is now standard procedure. You just watched China build the largest container ship ever made. 1,300 feet of ultra-high tensile steel, assembled from over 100 megablocks, each positioned with 2mm accuracy, all floating on engineering that had never been tested at this scale until the moment it touched water.